In this video, I'm going to return to a previous example in order to illustrate that the equations for electricity and magnetism that we have developed so far in this class are not yet a complete description of electricity and magnetism. So, here's the example. Imagine that we have a neutral conducting bar moving to the left in a magnetic field that points into the board. Now, consider the electrons in this moving bar. The electrons are little negative charges. They're moving to the left with this bar. So now if you look at the Lorentz force law, negative electrons moving to the left gives a vector QV to the right. We do QV cross B, and we get a force on those electrons toward the top of the bar. So the top of the bar is going to become negatively charged. Now, there's also a force on the protons toward the bottom of the bar, but the protons are locked in place by their forces within the bar, so they're not able to move. However, the electrons moving to the top of the bar leaves the bottom of the bar positively charged. Okay, so basically, having a neutral conducting bar moving through the magnetic field in this way basically gives us a potential difference between the ends of the bar. Great. But what if we considered this from a frame of reference in which the bar was not moving? So instead of having the bar moving to the left, imagine that instead we have this whole scenario moving to the right and the bar not moving at all. Equally respectable frame of reference. What would happen in that scenario? Well, there's still going to be a magnetic field, but now the bar is not moving. If the bar is not moving, the charges aren't moving. If the charges aren't moving, then they can experience no magnetic force. If they don't experience a magnetic force, it would seem there's no way to produce the potential difference that we observed in the previous reference frame. A quantitative explanation of this apparent paradox is beyond the scope of this video. However, I can offer you a qualitative explanation based on ideas we developed in a previous video. In a previous video, we considered a case where we had a field that was entirely magnetic in one frame of reference, but which was both magnetic and electric in a frame of reference moving relative to the first. Well, something like that is going on here. In our original frame of reference, we had a bar moving to the left against a stationary background. And we had a magnetic field that was pointing into the board and no electric field. And we had a magnetic explanation for why the top of the bar became negatively charged and the bottom of the bar became positively charged. In our new frame of reference, in which the bar is stationary and the background is moving to the right, we have not only a magnetic field, but also an electric field. Apparently, the electric field must have at least a downward component so that it can drive electrons toward the top of the bar. The electrons moving to the top of the bar leaves the bottom of the bar positively charged. And again, we have a potential difference developed between the ends of the bar. So, while we haven't developed a quantitative connection between all these things in class, we do, within the field of physics, have a quantitative resolution to this paradox. So it's not really a paradox at all. When you look at the full-blown picture of electricity and magnetism and special relativity. The equations that are fully consistent with special relativity are known as Maxwell's equations, and we will maybe explore some aspects of those later in this class. The equations we've been working with so far can be seen as approximations to those more general equations. Thank you.